Hi, everyone. Thank you for coming for our sessions. And today we will talk about flexible OpenSearch data management with Apache Iceberg. This pattern could be a solution for some challenges related to OpenSearch workloads, such as versioning and change to captures. And we talk about what is Iceberg as well, so don't worry about if you don't know so much Iceberg. So first of all, let us introduce ourselves. My name is Shuhei Fukami, and I'm an analytics solutions architect at AWS Japan. And also, I'm a co-organizer of Tokyo User Group of OpenSearch project.
Hi, I'm Sotaro, Shuhei's colleague, and I have been working with Data Lakes and Iceberg world for years. And recently, last year, I learned OpenSearch from him, and I became a big fan of that. And then we realized, hey, Iceberg could be really useful for operating OpenSearch. So that is why we are here today. Yeah.
Thank you. So this is our session's agenda. For today, we are going to start with confirmation that there are generally two ingestion patterns for OpenSearch, and we'll focus on one of them and begin by explaining what challenges are. And next, we'll talk about what Iceberg is or what elements of Iceberg. And also, we'll show you a representative use case of the Iceberg integration, and we'll show you some demos. So firstly, we'll confirm two general patterns. This is simply reviewing of the patterns, so I don't mean which one is better or not. So one of them is a direct ingestion pattern. This pattern is inserting data directly into OpenSearch from the data source without using an intermediate store. And as one example, this diagram shows us the architecture of this pattern, that data is directly linked from database to OpenSearch using CDC, change data capture. And through Kafka and Kafka Connect, when higher real-time performance is required, this pattern could be considered, I think. And however, this pattern tend to be a very tight coupling with OpenSearch and the data source, so which leads to extremely high management or operational cost in most cases. Okay, so next pattern is a staging pattern. This is today's topic. And in this pattern, putting a staging layer between the data source and the OpenSearch. The staging store is a typically used object storage like Amazon S3. And in this pattern, you can easily re-ingest or recreate index when the index is broken or something. Also, this pattern can be flexible processing, such as denormalizations or enrichment of your documents. So, while this is opposite of the previously mentioned direct ingestion pattern, but the trade-off is that data freshness or data ingestion lag. So today we will focus on this pattern's three challenges. First one is record-able delete and update. For example, when handling data containing personal information, it's necessary to have a capability to record level deletion or updates for compliance, such as GDPR. And OpenSearch has, of course, capability of deletion, so it's no problem. But it's necessary to do the same thing to the staging layer, staging stores. So this is not so easy task because files transferred from the source are stored in staging, and it's very difficult to narrow down which specific files contain the target records. And also, if you want to narrow down the target files, you have to need a have a mechanism to manage the location of records, and the mechanisms tend to be hardware. So, and additionally, records may exist in the multiple file like this picture. And in such cases, operations like deleting specific records become highly inefficient or require complex operations. Second challenge is data versioning. There are some situations that you may want to retain data for data each versions. And for example, in cases where you need to track the history of data, or you may have to use versioning or need to have a system or maintaining history. Additionally, when conducting accuracy verification with a search system or your search workload, or when you try to improving recommendations, you need to the versioning of data, because it's important to manage the test data or test corpus at the point of time for each experiment. So, like if you lost which data snapshot was used for experiments, later it may become difficult to investigate deeper on how the results were influenced by characteristic data and so on. So, when implementing data versioning, if you're managing data based on the PAR files, data source exports all the file every time. You need to keep all the files every time. So that's the only way to achieve this data versioning. So, and some object storage services offer versioning functionality, but they store all files background, so which cannot be cost-effective way in some cases. And even when using CDC, based on bin logs or something, reconstructing historical snapshot of table is required complex and difficult operations. And third challenge is difficulties in incremental or differential data management. And when data source has continuously records added or updated, deleted, in this situation, capturing changes between each file is not a simple task. So that's why all records are inefficiently reprocessed or re-ingest every time, sometimes. So when you ingest to OpenSearch, so it's necessary to implementing a complex job to manage record changes. So we have looked at the three challenges of storing patterns and staging patterns. And one of the solutions of this challenge is this topic, Apache Iceberg. So let's talk about the Iceberg overview a little bit. And anyone knows the Apache Iceberg is, or anyone is already use Apache Iceberg?
No one.
One? Only one? Two? Three? OK. Don't worry about it. We'll explain about what is Apache Iceberg. So, and Apache Iceberg is an open table format, and I think one of the most popular open table format. And it's high performance format for big data analytics. And that allows some feature for flexible data management like ACID transaction or time travel or rollback snapshots. And then Iceberg table can be changed schema like add columns or rename columns with object storage. So this is caused by table data structure that is efficient structure to adapt these operation flexible, and also Iceberg easily update or delete per records level. So let's go more deeper. So here I'll explain how Iceberg helps OpenSearch data ingestion, but the basic idea is using Iceberg table as a staging layer I mentioned. So data from RDBMS or some sources and goes to Iceberg table first and then to OpenSearch. So this is staging layer provides three main benefits here: process record level operation efficiently, or and retain data versions in a cost-effective way, and recognize changed events on data sources easily. And okay, here, what is Iceberg? So Apache Iceberg is one of the most popular table formats. This picture represents components of the open table format. And sometimes people confuse file format and the table format, but these are different layers of structure. Center of this picture is a table format. And file format is Apache or Ablo, or ORC, JSON, CSV, something like that. So that is the format of the data file, actual data file. And table format is the format how to organize data file and metadata file on the HDFS or Amazon S3 object storage. And that is a kind of rule where data file should be put or how to write them by engines. So Iceberg is also open table formats, of course. So various query engine can access to Iceberg table like top of this pictures. So include some distributed engine like Spark, Flink, Torino. These are commonly used as Iceberg engines. And also, single-processed engine can access and query Iceberg table, like Python client, which is called PyIceberg, or Iceberg Rust. And these are the summary of a table format. Okay, so this is Iceberg data structures. And how the Apache Iceberg data table is constructed, and these are the summary of the individual each layer. And the first layer is a catalog layer, and that catalog points the location of the latest metadata file. And if you update the Iceberg table, then Iceberg also updates the pointer of the table metadata file located in the catalog. And second layer is a metadata layer, and this layer is a kind of essential layer for some Iceberg features like snapshots or time travel. The metadata layer has three components: metadata file, manifest list, and manifest files. And this layer tracks all the operations of happening on the Iceberg table, and this layer enables specific feature like time travel or schema version because of this structure. And third layer is data layer, and data layer has actual data files and delete files. Delete files is not shown in this picture, but that tracks logical deletions. And Iceberg tables have a structure like this, composed of these layers. And I won't go into the details today, but this structure enables the Iceberg to achieve its efficient and convenient functionalities. I will explain these functionalities next. And I'll mention what's three functionalities of the Apache Iceberg. So first feature is Iceberg table can be efficiently referenced or updated or deleted by record level. And as I mentioned before, with the conventional way, just put a file, when performing operations such as delete, it is needed to explore all the files, through all the files. So this is because it's unclear which files are linked to the target records. So on the other hand, Iceberg makes efficiently to find target records by exploring only a narrow range of data files. And this is because a manifest file has a kind of the metadata and statistics of the table, and that enables efficient narrowing down of the record allocations. So, okay, next one is schema evolution. Iceberg has a feature called schema evolution. It can add or delete or rename and reorder columns and change data types through metadata changes only. And here's the thing. It means it's capable to change schema without rewriting existing data file, only the metadata file. So with this mechanism, Iceberg tables schema can be flexible and easily modified. So this is a very effective feature for some cases, such as CDC patterns, where the source schema can be changed. So third one is one of the most popular feature, I think, of Iceberg, time travel. By snapshots, Iceberg tables can be logged over the changes made to the data over time. With time travel queries, it is enabled to access data from a specific point in time or reference any particular snapshot. So additionally, Iceberg table can be rolled back to a previous snapshot if needed. So and look at this picture. For example, when executing a time travel query specifying snapshot 1, the center of the metadata file, which is shown as S1, the engine first refines the metadata file of the snapshot 1 and to locate the manifest list and point it to the by snapshot 1. And through this process, it then refines the necessary manifest files and data files. And this allows the querying of data associated with specified snapshot. And if snapshots are always specified instead, a different set of data files are referenced. So here's the thing, that this structure allows for efficient data management where unchanged data is shared across snapshots. So while only storing the differences in separate files. So this means this approach enables cost-effectively versioning of data. I sense I'll explain 3 features, but actually 4. So and the first one is a change log view. And this is implemented as a Spark procedure. And this procedure performs complex operation, change data capture, including updates and deletes. And using this procedure, you can create a view called change log view that maintains a history of table changes. And look at this picture. And for example, first left side. And let's insert a single record into an empty table. And next, we update the value of the record rating column. And so the change log view for this table will appear as shown on the right side. So this shows how record changes, and this can show delete operation on same way. So you can see the history of the operation performed on the table along with the contents of those records. So using this change log view, it's also possible to identify the difference between snapshots. So far, we've looked at the features of Apache Iceberg. So now Sotaro will explain how this capability can be used as a pipeline of OpenSearch.
Yeah, thank you, Shuhei. So as we walk through, thanks to these kind of Iceberg features, Iceberg can work as a useful staging layer between data sources and index. But how do Iceberg and OpenSearch actually work together? Well, since Iceberg is an essentially open table format, any tool that supports Iceberg can read and write it. But when it comes to working with OpenSearch, I'll introduce 2 major client options today. The first one is PyIceberg. This is a Python library for working with Iceberg table. What's nice about it is that it provides a really straightforward way to use Iceberg. All you need is Python, and it will work in any environment where Python can run. And it integrates with data science libraries like Pandas and Porous, which means you can work with Iceberg using familiarized tools. And of course, since OpenSearch also has solid Python library, you can easily read from Iceberg table and then index them into the OpenSearch. So here's a simple example. Let's save a CSV file into our Iceberg table. First up, we load the CSV file using PyData PyArrow library. Then we create an Iceberg table. The schema is automatically inferred. After that, we just insert the data into the table. And finally, we can check what's in the table using toPandas method, and that's it. With just these few lines of Python code, we have created an Iceberg table on the storage. Then let's index this table data into OpenSearch. So first, we load the Iceberg table and convert it to pandas. This process is thanks to PyArrow zero copy, so it's very efficient. Then we connect to OpenSearch using Python client. Then we index the data. Pandas to OpenSearch method handles everything. So that's all. Our Iceberg data is now searchable in OpenSearch. So PyIceberg is good for lightweight deployment and Python-based data pipelines. So let's discuss another client option, Spark with OpenSearch Hadoop. And basically, OpenSearch Hadoop is one of the OpenSearch projects, and it is a library that connects OpenSearch with MapReduce, Hive, and Spark. And now when it comes to working with Iceberg, Spark is particularly important here because it's one of the most mature clients for Iceberg. In fact, some Iceberg features like changelog view are only available in Spark so far. In addition, Spark provides strong distributed processing capabilities that handles large datasets really well. So this option shines when you need both scale and advanced capabilities. So here's how Spark with OpenSearch Hadoop work with distributed processing. When Spark reads data from the Iceberg table, it distributes the work across multiple tasks. Each executor runs these tasks in parallel. It means processing different parts of the data. And here's the key. Each task writes directly to OpenSearch in a distributed manner, so it can handle large-scale data really efficiently. So again, here's a simple example, this time saving a Parquet file into Iceberg. First up, we read the Parquet file like this. Then we write it to an Iceberg table. We specify the table name and storage location. Notice that using Iceberg parameter here, that's what tells Spark to create an Iceberg table. And now we can query the table with standard SQL syntax. As you can see in the result, our data is now stored in the Iceberg table. Then let's index them. First, we read the Iceberg table with Spark SQL. Then to write to OpenSearch, we need to set up the connection options like OpenSearch cluster endpoint or port and index name and so on. And that's all. Spark reads from Iceberg and write to OpenSearch. Then our data is now searchable. It is really straightforward, isn't it? And here's a useful tip. When Spark writes a data frame to OpenSearch, we can use a column value as a document ID. So by specifying the doc ID, we can achieve upsert functionality. So if a document with the same ID already exists, Spark will update it. Otherwise, it will insert a new document. In this way, Iceberg can work with OpenSearch really well using PyIceberg or Spark. Then, from here, let's discuss 3 representative use cases for Iceberg with OpenSearch. Today, we will introduce these 3 use cases, data versioning, change data capture, and continuous schema change in detail with the demo. These use cases address the many common challenges we see in such data ingestion pipeline. Yeah, please.
So me again. I'll explain about some use cases. The first use case is data versioning. So let's imagine a scenario where you're repeatedly running experiments to verify search accuracy, or you're developing the recommendation models. In such cases, it's often required to manage which test data was used for each experiment. And in this scenario, you can use Iceberg to versioning your data and then index the historical data in OpenSearch. So for reproduction experiments, and as Sotaro mentioned, Spark and Python as the main client options that can be used in this situation. And for this demo, we'll be using Python client, PyIceberg and OpenSearch ML. And in this demo, using the so to ingest the historical data into OpenSearch. Okay, so okay, now firstly, I'll query the Iceberg table here by the PyIceberg. Looking at this closely, this set is a movie data set, and Frankenstein's rank is the top. This is kind of weird, you know. So next, I'll query and I'll represent the snapshot of this table. And there are 3 tables in this table, and three snapshots in this table, and that means this table has been changed twice. And also in this scenario, I want to use all the snapshots. So here I specifying all the snapshots. So this is all the snapshots table. And here on Frankenstein's ranking is not top, so it seems there are some passionable fans of this movie. And also I'll ingest to the OpenSearch from this snapshot, all the snapshots table. And so I'm using the OpenSearch ML and directly ingest the Iceberg table's data to the OpenSearch index. So next I'll query the OpenSearch index here. So we can see the past data has been correctly ingested. Okay, so in this demo, I'll show you it's easy to ingest the OpenSearch from the Iceberg table with snapshot IDs. Okay.
Yeah, thank you. So let's discuss another use case and change data capture. So one of the major data sources for OpenSearch is databases, and we often need to replicate those database records to OpenSearch with CDC style. But when you add a staging layer between them, you run into some implementation challenges sometimes. First, you need to efficiently handle continuous row-level updates and reads from your CDC stream. This is difficult with simple file-based staging pattern. But there is another critical challenge. You need to track what actually changed between versions to properly update OpenSearch. If your staging layer only keeps the latest state, you can't tell which records need to be deleted or updated in the index. So managing both of these requirements with simple file-based approach becomes practically difficult at scale, but Iceberg handles both naturally. I will introduce example architecture and data flow. Division capture change events from the source database and send them to Kafka. Then a Spark job below consumes those events and reflects them in the index table on the storage, Iceberg table on the storage. This way, we are replicating the source database on our storage layer, and since it is in Iceberg format, we can use it from various tools as needed, including OpenSearch. Then, another Spark job above read from this staging table and reflect the changes to OpenSearch. The key point is that Iceberg provides a changelog view, which tells us exactly what happened at the record level. So this second Spark job can easily identify what needed to be updated or deleted in the index. Okay, so I'll show the demo. Yeah, in this video, 2 records have already been replicated from MySQL to OpenSearch via Iceberg. Yeah, there are two records, and this SQL editor is connected to MySQL, and this is some kind of movie-related table. And yeah, this console is connecting to Iceberg using Spark, and you can see same records like this. And you can see the same documents on the OpenSearch as well. So, okay, so let's make some changes to the source tables. I updated the one records to rank 2 and deleted the other records. So now a source table has only one record. And this is a Kafka UI. And Debisim capture database changes and sends them to Kafka. And we can observe that there are two change events here. And one describes the record updates rank to 2. And the other event describes the delete event. So after is null, it means deleted. So to consume these events, I wrote some Spark script. This main part of the main part of this code is a merge statement. It reflects database changes to Iceberg from the Kafka events, like this. And I actually already ran this script on this terminal. And as a log says, one record is updated, and the other record is deleted. And we can confirm these changes on the terminal, on the Iceberg. As we can see, on the Iceberg, one record is deleted, and the other record's rank is updated to 2, like this. And here is a changelog view. It tracks what happened in this table at the record level. So we can observe each record, what record is updated and what record is deleted in detail. And for update, we can see before and after for the record values. So I wrote another Spark script. It uses changelog view like this. So it tracks what happened on the Iceberg table and reflect it to the OpenSearch. Before run this script on the OpenSearch, there are still initial 2 records like this. And let's run this script. Okay. Okay, and after our script runs, one record is deleted, the other record is upserted log side. So let's match all again. Now on OpenSearch, one document is deleted, and the other document's rank is updated to 2. So overall, now we achieve sync between the source database, the staging Iceberg table, and the OpenSearch index. All 3 stay in sync. This is how you implement CDC using Iceberg's unique characteristics. Yeah, next use case.
Okay, third use cases is dynamical schema changes from source DB to OpenSearch through staging layer using Iceberg. This scenario is where you're using CDC to sync data from a database to OpenSearch as well. In these cases, managing the schema in the pipeline can be challenged when the source schema changes. So, but Iceberg can be dynamically modify the schema, which is enabling a flexible data pipeline in this demo. And no, so in this demo, using Debisim to connect the database CDC to Kafka, the same as the previous one, and then using Spark structure slimming to ingest data into Iceberg table. On certain with the option enabled to dynamically adjust the Iceberg schema to match the CDC records. And finally, retrieve only the change of the data from the Iceberg table and ingest to OpenSearch. Okay, first, let's query the source table. This is the same dataset, a movie dataset. And also, I'll show the columns of the table and ID to actors. So next, I'll query Iceberg tables too. And this table has been already synced with the source table. And record count is 0 to 18, so 19th, actually. And these are the columns of the Iceberg tables, and these are the same as the source table columns. And also, I'll show you the OpenSearch index, and this index has been already synced with the source table through the Iceberg table. So now, also, I'll show you the mapping of the table. Sorry, mapping of the index. So now, I'll try to alter table and add columns. The name of the column is a new column. It is obviously new column. And also insert the two records with a new column. And inserting two records here. And soon I'll query Iceberg table again, and we can see one of the records is already added, and the schema is dynamically changed. And here's because of the lag, I'll query again the Iceberg table, and we can see another record is added here. And also, the Iceberg table's column is changed here, and new columns is added. So finally, I'll try to sync with the Iceberg table to the OpenSearch index. So this is a Spark jobs, and this Spark job load from Iceberg table and ingest to the OpenSearch. So here, we can see the document count is changed to the 21. But two documents is added. So and mapping field, new column field is added here. So in this demo, I'll show you how to sync with the schema dynamically through Iceberg tables. Last.
Yeah, that's all about use case. And let's summarize what we have covered today. So basically, when ingesting data into OpenSearch, a staging layer between source and index help you manage data more flexibly. And Iceberg serves as that staging layer. It's an open table format, and it achieves some database-like capabilities to your storage. And so by using Iceberg as your staging layer, you can build much more flexible and maintainable OpenSearch ingestion pipelines. Yeah, unfortunately, we don't enough time to QA discussion, but anytime, please talk to us after this session. Anyways, thank you for your attention.